Swayam Prabha. Digital India. Educated India.
Well, in the last class I discussed about the sequences of various events that happen during the course of polymerization of an olefinic monomer in presence of some initiator. I discussed that initiator needs breaking into free radicals and those free radicals initiate the monomer and continue propagation. After propagation, next step is termination of the propagating free radical, which is known as growing chain radical. So, you have seen sequences of events like initiator decomposition followed by initiation of monomers for polymerization. Once a monomer molecule is initiated, then it starts propagation to form bigger chain molecules. A time comes when those bigger macromolecular chain radicals combine or annihilate with each other to form a dead polymer molecule. So, there are events like initiator decomposition, initiation, propagation and termination of the growing chain free radicals. Of course, each and every step in this process of polymerization has its own kinetics, each are guided by its own rate constant. So, if we want to evaluate the kinetics of polymerization involving olefinic monomers for addition chain polymerization, you have to consider the rates of decomposition of initiator, rate of initiation, rate of propagation and rate of termination. So, we see here that rate of initiation and initiator half life will let us discuss today. You know what is half life of initiator? That means time required for 50% decomposition of the initiator, that is the half life. You have seen one initiator molecule decomposes to form two free radicals and decomposition rate constant is designated by Kd. So, from here you see the rate of initiator disappearance is expressed as minus d I by dt is equal to Kd into initiator concentration I0 I, or I is equal to I0 e to the power minus k dt, applying limiting and boundary conditions. At t is equal to 0, I is I 0, and at any instant of time what is the initiator concentration, that can be evaluated from this relation. Now, by setting the initiator concentration at any instant of time, when the initiator molecules 50% of the initiator molecules have been decomposed, that is the, if that is put in this equation, we get half life of the initiator at a particular temperature, of course, that is equal to 0.693 by K d. This is a well known relation in every case of these decomposition reactions. Now, the rate of initiation, the rate of when the primary radicals are formed from the decomposition of an initiator molecule, those primary radicals interact with monomer to initiate a polymer chain. Now, the rate of that initiation is expressed as R I is equal to 2 into F K d into initiator concentration. Now, F is a factor, it is a factor of efficiency factor. What is, why this efficiency factor is included in this equation, in this rate equation? Because once an initiator molecule is thermally decomposed, now their thermal decomposition efficiency comes into play. At the same time, it is not always true that once a radical is produced, free radical is produced, that free radical is capable of initiating polymerization. So, two things: efficiency of decomposition of initiator molecule as well as efficiency of initiation of monomer molecules by the generated primary free radicals. These two things, please do not confuse. Okay. So, in the decomposition step there is one efficiency parameter, in the initiation step there is also another efficiency parameter. So, when a polymerization is started, it is not that true always that all the initiator molecules which have been taken used for the polymerization, that decompose initially, that slowly decomposes, that takes time depending on its half life and temperature, it decomposes. Okay. As soon as it decomposes, it is not always true that all the primary free radicals produced from the decomposition of initiator will initiate the polymerization 100%. So, these efficiency parameters comes. So, here the rate of decomposition of initiator, that is equal to twice F K d I, and that is equal to rate of initiation is same twice F K d I. So, what will be the rate of polymerization? Now, the rate of polymerization depends on this monomer disappearance. So, the monomer disappearance rate is expressed as minus d m dt, where m is the concentration term, that is the sum of two rates, rate of initiation of monomers as well as rate of propagation. You have seen the propagation steps. Let me go back to this. Here you see this is the decomposition step, initiator decomposition step, this is the initiation step, this is the these are the propagation steps. All these propagation steps proceed at the same rate. So, in every case you see only one rate constant is included here, K p. Then termination, where we term this termination rate constant as K T c if it is terminated by coupling reaction, coupling of two growing free radicals, or if it terminates by disproportionation reaction, So, we term it denote it as Ktd. Here the molecular weight is lower in this case, where the molecular weight of the polymer is bigger, and ultimately overall, if we consider the overall termination involving two growing chain free radicals, we call it a dead polymer molecule. So, this termination step is a death activity, killing activity of the propagating polymer chains, propagating polymer free radical chains. So, here you see since the number of monomer molecules in initiation step is far less. Now, here I have shown this rate of disappearance of monomer can be considered as the rate of polymerization, because here monomer is disappeared to form a polymer. So, if we measure the rate of disappearance of monomer, then we can find out the rate of polymerization. Now, as it is shown that this rate is the sum of two different rates, rate of initiation, because in the initiation step monomer is also disappeared, and in the propagation step monomer is also disappeared. But since in the monomer your initiation step the consumption of monomer is far and far less than the consumption of monomer in the propagation steps. The physical significance is like this: once the initiator molecules are decomposed, producing primary free radicals. So, at any instant of time there may be plenty of primary free radicals in the system. So, simultaneously one can expect initiation of many polymer chains. Okay. In those initiation steps only one monomer is involved, whereas when all those initiated monomer chains starts consuming monomer in the propagation step. So, the consumption of monomers, overall consumption of monomers in the propagation step is far and far ahead of this monomer consumption in the initiation step. So, that R I in this expression, in this rate expression, if it is neglected, there is nothing wrong. So, overall rate of polymerization R P can be expressed as overall disappearance of the monomer minus dm by dt. So, it can also be expressed as R P is equal to rate constant for propagation K P, growing chain radical concentration into monomer concentration, where the concentration of the monomer is very less, concentration of this growing chain is very less. It is so transient, that even once it is initiated, so within a very short period it completes its growth and gets terminated, becomes dead. So, in the at any instant of time, if one measures the concentration of the growing chain radicals, it is very less, although it is very difficult to measure again. There is no experimental technique available till date that such concentration of such transient intermediate species can be evaluated. Now, in order to calculate or evaluate this rate of propagation, we have to know these parameters K P, m dot and m. That means concentration of monomer at any instant of time, unreacted monomer of course remaining, and m. Now, this can be estimated. The quantity of monomer present at any instant of time can be estimated. There are procedures, but how to estimate this thing? As I mentioned, its concentration is very less and so transient that it is very difficult, it is almost impossible. But although I have said it is not so stable, but it must have adequate stability for colliding with a monomer molecule for the growth activity, for the propagation. You should not confuse with that, although it is very fast, that is why its concentration is less, but it has got sufficient stability, that means stability of the growing chain radical through the resonance stabilization, hyperconjugation, other things I have shown earlier. That way it is stable adequately, so that an incoming monomer can collide with this growing free radical site and add on to it. Otherwise, one cannot get a polymer chain, one cannot get a polymerization product. In order to evaluate this concentration, a steady state assumption has been done. What is that? That is the rate of change of concentration of growing chain radicals quickly becomes 0 and remains 0 during the course of polymerization. Rate of change of concentration of radicals quickly becomes 0 as well as remains 0 during the course of polymerization. If it is elaborated in this way, that once a growing chain is initiated, eventually it is converted to a macromolecular chain and it is terminated. So, if we assume that rate of initiation is equal to the rate of termination, in other way we can take this concept of steady state. At the steady state, rate of initiation becomes equal to rate of termination. Now, let us see what are these rate of initiation and rate of termination. Now, rate of termination is twice k T m dot square. This factor of 2 here is due to the fact that during this termination 2 growing free radicals are involved in this termination process. That is a convention. Since 2 free radicals are involved in the termination step, so this factor of 2 has come, and this m dot into m dot square. So, from this relation one can get the concentration of this growing free radical chain is equal to R I by 2 k T under square root. Okay. And since R I is equal to twice F k d I, one can, after substituting this concentration of m dot square growing chain radical concentration here in this equation, you can get this expression after substituting, or this expression, where this efficiency factor has been included in the rate equation. Okay. So, this is the overall rate of propagation, overall rate of polymerization. You should not forget this thing. So, R P is equal to rate constant into the monomer concentration term into efficiency factor into rate of decomposition of the initiator into initiator concentration divided by rate of termination rate constant. Should be half over here. It cannot be done now, somehow it was there. Do not worry for these things, these minor things. It is square root is there, of course, R I by twice k T, F k d I by k T. So, this is the overall rate of propagation, overall rate of polymerization. Once again I repeat, R P is equal to K P m F k d I by k T to the power half. Okay. Now, the question is how this rate of polymerization is experimentally followed, how it is evaluated. Well, you can say, sir, you are showing us with the help of these expressions or equations that this is the way to get this rate of polymerization, but how to experimentally evaluate it. Suppose you are given this assignment of synthesizing polymethyl methacrylate or polyvinyl chloride or polyvinyl acetate in the laboratory. If I ask you to evaluate the rate of such polymerization, how to evaluate? Okay. That means, you have to go through by measuring the change in any of the property that differs for the monomers and polymers. Now, that property may be solubility, that property may be density, that property may be refractive index, that property may be specific volume. So, there are instruments like very simple instrument, even you can fabricate in your laboratory. You prepare a dilatometer or dilatometer. It is nothing but a very small bulb, glass bulb connected with a capillary. You know, you have seen this glass thermometer. In the glass thermometer, there is a bulb filled with mercury connected to a capillary. Okay. So, this rise of this mercury thread through the capillary helps us to measure the temperature of a system. It is simply like it is similar kind of thing. So, you can prepare a dilatometer, you fill the dilatometer with the monomer and initiator or monomer initiator solution, or you can take in a solvent also. Then you place that dilatometer and close it, and then place that dilatometer in a thermostatic bath, which can maintain a constant temperature. Then raise the temperature of the thermostatic bath to the decomposition temperature of the initiator, say 80 degrees Celsius for benzoyl peroxide. What will happen? Benzoyl peroxide will decompose and will initiate polymerization. As soon as it starts polymerization, initiates polymerization, it will convert the monomer to polymer. Once it converts, monomer is converted to polymer, there will be volume shrinkage in volume. So, that volume shrinkage can be read from the capillary scale of the capillary. That can help you to measure the change in volume or as well as the change in density, like that. Okay. Or you can say you carry on this polymerization in sealed ampules. You have seen medicines, liquid medicines for hypodermic or intravenous injection is available in sealed ampules. What we do? We break open the ampule and suck the liquid by hypodermic syringe, then we inject in the body. Okay. So, similarly, here also you take this monomer initiator in an ampule and evacuate it by freezing in liquid nitrogen temperature. It will be frozen. After it is frozen, liquid is frozen, then you connect it to a vacuum line, evacuate the oxygen, air, then in that evacuated condition you seal it. So, you can have several sealed monomer filled sealed ampules, evacuated sealed ampules in many numbers. Okay. Then you place all those ampules, monomer filled ampules, in a thermostatic bath. Raise the temperature of the bath to the decomposition temperature of the initiator. Okay. Then you take out the sealed ampules time to time after certain specific time intervals of 5 minute or 10 minute or 20 minute intervals. Take out it and freeze it, so that you arrest the reaction by freezing. Okay. Break the ampule and pour the liquid in a non-solvent. What you will see? The polymer which has been formed within the ampule, it remains soluble in the unreacted monomer. When you pour that polymer solution in non-solvent like methanol, suppose, So, you are polymerizing methyl methacrylate into polymethyl methacrylate. Okay. That polymethyl methacrylate remains dissolved in methacrylate methyl methacrylate monomer. So, you are pouring a polymer solution in methyl methacrylate into a non-solvent like methanol. As soon as you pour it, immediately it will precipitate out, it will solidify. Okay. This way, say in the first, after the first interval of 20 minutes, you have taken the first ampule, you have poured in this non-solvent, you have got a solid precipitate of polymer, then you filter it quantitatively, wash it with solvent, fresh solvent to remove the unreacted monomer, then you dry it and take the weight. And you know the quantity of monomer was contained in that ampule. From that you can calculate how much monomer has been converted to this solid polymer. Then you take the second ampule, take out the second ampule which has grown further to that of the first one. Repeat the same process, isolate the solid polymer by pouring in non-solvent, wash it, dry it, take the weight. This way you will have samples like say 10 samples suppose, and you will find that starting from sample 1 to sample 10, you will find that the amount of polymer you have got will be different, will be gradually more and more and more. So, that can also help you how much polymer that will give you the conversion, percent conversion, and that percent conversion you know the time at what, after what time you have taken out the ampule from the thermostatic bath, you know the time. So, amount of polymer you have got after that time, from that you can calculate the rate of polymerization. So, that is the way. Another way, if you do not have any sophisticated instrument, this is the simplest way available to you in the laboratory. You can carry out the, you can evaluate the rate of polymerization of that particular monomer. Or if you have some instrument like say UV or other spectroscopic instrument, with the help of those spectroscopic instrument, you can also evaluate the rate. Now, in a dialectrometric experiment with the taking the help of a dialectrometer, based on density change by volume contraction, in cases of vinyl chloride polymerization and methyl methacrylate polymerization, this was the density of the monomer, then density of the polymer. So, volume change is this. From this volume change, which is proportional to the growth, that way one can calculate the rate of polymerization. Am I clear? Then this shows a square root dependence of rate of polymerization on initiator concentrations. Now, many people have done extensive research on this effect of initiator concentration on the polymerization rate, effect of monomer concentration on the polymerization rate, effect of temperature on the polymerization rate, effect of different initiators on the polymerization rate, effect of presence of different solvents in the polymerization, all these things. We do not have that much of scope for discussion of those details in this particular course, but just I mention you that the question should automatically come, sir, what would be the optimum concentration of initiator which should be taken for polymerization of one particular monomer, whether one particular initiator will be suitable for all the monomers for polymerization. So, these questions automatically comes. The answer is no. It is specific to a specific system of monomer and initiator. An initiator used for polymerization of vinyl chloride may not be efficient for polymerization of methyl methacrylate, may not be so effective for polymerization of styrene, may not be so effective for polymerization of acrylamide. Do you understand? So, this is the situation. Not only that, what is the effect of temperature of polymerization? What is the effect of initiator concentration? Even if one initiator is selected as an efficient initiator for one polymerization of one monomer to get a polymer of that monomer, then what is the optimum concentration of the initiator which gives you maximum conversion as well as desired molecular weight or highest molecular weight as well as highest rate, that is to be evaluated. Okay. Those works have already been done for many monomers, but for your understanding, for your information, just I am mentioning here a case where monomer methyl methacrylate was polymerized in presence of benzoyl peroxide at 50 degree Celsius, and vinyl benzoate, another monomer, was polymerized using azo-bis isobutyronitril azo initiator, azo-bis isobutyronitril at 60 degree Celsius. So, this is the rate behavior. This is a schematic drawing, all those scales are there, this is not to the scale, it behaves like this. Now, in order to evaluate this thing, rate as well as other parameters, just you see, you select different concentration of initiators, you see this is another one concentration, this is another concentration, this is another concentration like this. So, different concentrations are selected of this initiator, this is benzoyl peroxide, it breaks over here, and ultimately what happens? Carbon dioxide is released and some phenyl radical is produced. So, both this radical as well as this phenyl radical, they initiate the polymerization, and this is the overall rate of polymerization. Now, in order to know the dependence of polymerization rate on initiator, a plot of Rp versus initiator concentration, as you have shown earlier, you have seen earlier, if that is plotted, then this is the slope of the curve, this is the slope of the curve. Okay. So, if you know these parameters Kd, Kt, monomer concentration and Kp, so you can calculate the initiator efficiency factor, F factor, value of F factor. Okay. Or if you know this F, Kd, Kt, M, then you can evaluate this Kp. So, this is the way, by just measuring the rate of polymerization, and if some other parameters are known, some unknown parameter can be calculated from this polymerization. Just I have mentioned that in general that an initiator decomposes to produce two primary free radicals. What are those initiators and how they are decomposed? That means, they must be excited by different forms of energy, maybe thermal energy, maybe light energy, or maybe chemical energy. So, here only 3 cases are mentioned, say thermal initiation by thermal excitation of the monomers initiators. Those initiators decompose to form primary free radicals. Those primary free radicals initiate a monomer to form a polymer. You should ask a question, but you are not asking question, that is, if we do not use initiator, what can happen? Can you get a polymer? Is there any real necessity of initiator? Can only this monomers form polymer without using an initiator? Answer, yes or no. If we do not use an initiator, can we get polymer from a monomer? That is one stimulation you are giving. I am telling that if we do not use an initiator, yes, that is one way. Other than radiation, he has given some clue. Can olefinic monomers undergo polymerization without using any initiator? How? Of course.
By homolysis of the double bonds.
How?
By the supply of the proper energy which can break the double bond homolytic.
What is that form of energy?
Heat.
Heat, right. As he told that either radiation, magnetic radiation, or thermal stimulation, both can initiate polymerization and can help getting polymer, but that polymerization is not easy to control, that polymerization kinetics. Say if you keep a monomer within a bottle, within a container at ambient condition for prolonged period, that monomer can start polymerization within the container, and after some time you will find that entire monomer has been converted to polymer, solid polymer. It happens. In the laboratory, if you keep methyl methacrylate or styrene in a bottle on the rack, you will find after 6 months of time that entire monomer has converted to a solid material, that is polymer, polystyrene or polymethyl methacrylate. For that reason, that monomer needs stabilization by putting inhibitor. Why that happens? Because in this ambient condition, the temperature varies from say 20 degrees to 40 degree, 44 degree, like that. So, that temperature can slowly initiate the monomer by simply, as he told, that thermal homolysis of the olefinic double bond. Once a double bond is opened, that will initiate the polymerization for so many monomer radicals, polymer chains.
In that case, did it store impurity also reduce the activation energy?
Of course, if the monomer is not pure, if there is impurity, that impurity can also start polymerization. So, monomer should be stored in a pure condition, as well as it should be stored with the help of an inhibitor. That means, you have to add certain inhibitor. For example, these monomers are stored with hydroquinone. Hydroquinone is an inhibitor molecule. What is the role of inhibitor? Now, if there is a possibility of breaking a monomer molecule, thermal homolysis of the monomer, olefinic monomer double bond, that free radical will be scavenged or stopped by interacting with this hydroquinone radical. So, that inhibits, even if there is initiation, that inhibitor will inhibit its growth, that is called inhibition. Okay. So, thermal initiation is possible, photochemical initiation is possible. So, if electromagnetic radiation, if a monomer is exposed to electromagnetic radiation, that means energy should be sufficient enough to break that olefinic double bond, that may be in the form of heat, maybe in the form of chemical energy, or maybe in the form of electromagnetic radiation. Now, initiator characteristics are, it should be readily available, should be stable under ambient or refrigerated conditions, so that this initiator does not start decomposition, should possess a practical rate of radical generation at temperatures less than 150 degrees Celsius. Otherwise, if the polymerization needs to be carried out at high temperature, then the cost of the polymer will be high. It is convenient, it will be economic, it will be convenient as well as economic if the polymerization can be carried out at lower temperature. There are various reasons. We can save energy if we polymerization at lower temperature. At the same time, if we carry out the polymerization at higher temperature, what will happen? It can give you higher productivity, although at the higher cost it can give you higher productivity, but that will lead to random kinetics, uncontrollable kinetics of the polymerization. What can happen? During polymerization, a polymerization reactor can explode, because such polymerization reactions are highly exothermic in nature. If there is acceleration of rate of polymerization at any instant of time, eventually at any moment there will be huge accumulation of huge quantity of heat, within the reactor. If that heat could not be dissipated from the reactor, that reactor will explode. So, those are the problems and difficulties. So, in order to avoid all those problems, it is better to polymerize at lower temperature, which can be controlled, that will remain at your control, entire polymerization kinetics. So, it is advisable or it is better if the polymerization is carried out at lower temperature, although polymerizations are carried out at higher temperature for some cases, say in the gas phase olefinic polymerization, say polymerization of ethylene, propylene, etc. If you look into literature, you will find that your technology of manufacture of polyethylene and polypropylene at high temperature gas phase polymerization. Thermal initiators contains OO bonds, SS bonds, NO bonds that possess desired range of dissociation energies, which lie within this value 100 to 170 kilojoule per mole. So, chemical compounds having such bonds can act as initiator, thermal initiators. Okay. Now, if you take peroxide compounds as thermal initiators or azo compounds as thermal initiators, is acyl peroxides such as acetyl and benzoyl peroxide, alkyl peroxides such as cumyl, and tertiary butyl peroxides, hydroperoxides such as tertiary butyl and cumyl hydroperoxides, per esters such as tertiary butyl perbenzoate, azo compounds such as azo-bis isobutyrylnitrile 22 prime azo-bis isobutyrylnitrile, where it contains CN bond, that this energy is CN bond disenergy is quite high, but NN bonds breaks, and disulfides or thiols, organic thiols, that can also be used as initiators for polymerization of olefinic monomers. Half lives of peroxide initiators, you have already seen how that can be calculated. Knowing half lives of initiators, it helps to select a suitable initiator for one particular system of polymerization. Redox initiation. What is redox initiation? That redox initiation is more advantageous than thermal initiation, because redox initiation can be carried out at very low temperature, lower than ambient temperature even. Say if you take hydrogen peroxide and ferrous system, ferrous salt and hydrogen peroxide, that produces ion as well as free radical. Okay. Because the hydrogen peroxide on homolytic decomposition forms two free radicals, and that interacts with ferrous ion. So, it will be oxidized to ferric and one anion and a free radical will be produced. that free radical initiate polymerization, and that is done at very low temperature, at ambient temperature. That means, from 0 to 50 degree Celsius temperature. At 0 to 50 degree Celsius temperature, this redox system can occur, or say persulfate, potassium persulfate, ammonium persulfate. These can be used as oxidant instead of ferric. That is also a free radical polymerization. Let me give you example of polymerization of styrene and butadiene, copolymerization of styrene and butadiene. The styrene butadiene polymerization can be, copolymerization can be done in bulk, can be done in solution, can be done in emulsion. Again, that emulsion polymerization can be done at higher temperature, can be done at lower temperature, and you will find later, not now, we will cover in this course that styrene butadiene rubber, that is manufactured by two major techniques, cold technique and hot technique. Hot polymerization is carried out at around 50 degree Celsius temperature using this redox initiation system, as well as that cold polymerization of cold copolymerization of styrene and butadiene, that is also carried out at lower temperature, say 5 to 10 degree Celsius temperature, cold polymerization and hot polymerization. Now, it has been found that polymer obtained through cold polymerization carried out at 5 to 10 degree Celsius gives better quality of rubber, better quality of styrene butadiene rubber. Cold polymer is better, gives high molecular weight at higher rate, as well as excellent molecular weight distribution. This gives the same thing, a general system of peroxides, acyl peroxides, etc. Okay, and decomposition into free radicals and ions. Other reductants which can also be used, say chromium, vanadium, titanium, cobalt and copper in the reduced state. The redox system has a much larger decomposition rate, it occurs at low temperature, and rate of redox polymerization gives you very good rate at this temperature range, and this rate of redox polymerization can be calculated or can be evaluated with the help of this expression. You can compare, why I have shown this thing, you can compare the rate of polymerization using thermal initiation, as you have seen Rp is equal to Kpm F Kdi by Kt to the power half. Here you see Kpm, efficiency factor is not there, Kd, reductant concentration, oxidant concentration by twice Kt to the power half. Here the efficiency factor, decomposition factor, that is not included here. That is the difference between that rate expression with this redox polymerization rate expression. Photochemical initiation, monomer, the monomer, and this is the light H nu, and this is the excited state of the monomer when it absorbs that light of a suitable wavelength. Okay. Now, this once this monomer is excited by light, the dissociation, the bond of that monomer, pi bond, that dissociates, producing free radicals R dot, R prime dot, okay, and that initiates polymerization. Now, there are other considerations too. You have seen in case of thermal initiation that sequences of events, that you have seen that primary radical R that adds to the monomer at the initiation step, forming an initiated radical. This R m dot adds to another monomer, forming Rm2 dot, Rm2 dot plus M Rm3 dot. This way it continues till we get R M n dot. Likewise, we can get R M m dot, and in the termination step we get R M m plus n R. So, look at the chemical nature of this polymer. Here M we are having a chain of M at the end one R group, here at the end another R group. What is this R? These are initiator residue. Initiator residue that remains attached to this polymer chain. So, if you take benzoyl peroxide, the benzoyl peroxide will give a polymer product with this. But if it is done by photochemical initiation, this initiator residue will not be there. Of course, this can be in one way advantageous in order to study the course of polymerization. If it contains one isotopic level or a functional group which can be estimated, say functional group F suppose, which can be estimated, then that can help you to count the number of polymer chains that have been produced, as well as to calculate the molecular weight of the polymer chain that has been produced. So, these are various considerations which can automatically arise. Now, here in this case of photochemical initiation, as before, you can compute the rate of polymerization in a similar fashion, where monomer concentration term is there, rate constant of polymerization is there, and phi I A by k T to the power half, where I A is the intensity of absorbed light in moles of light quanta per liter second, or Einstein, and this phi is the number of propagating chain initiated per light photon absorbed, or quantum yield for initiation of polymerization. There is another way of polymerization principle, that is plasma polymerization. Now, this plasma polymerization today has become very important to the semiconductor or electronic industries, semiconductor people or electronic people, for making devices. Plasma polymerization. Why? Now, in the way of fabricating device, semiconductor device or microelectronic device, there if you want to use a polymer, then the processing of that polymer leading to that microelectronic chips or semiconductor your device, then you have to have a very thin film involving very small quantity of polymer, which is very difficult to fabricate by taking a polymer synthesized in this fashion. So, people try to deposit that polymer on the electrode or on a substrate in a very thin film form, say thickness may be in the nanometer range, nanometer scale, say suppose it may be 10 nanometer or 5 nanometer or 20 nanometer, like that. To make such a thin film using this polymer produced by this fashion is very difficult. That sophistication may not be achieved. For that purpose, people go for plasma polymerization. What is plasma polymerization? The principle is same. Now, you take the monomer, raise that polymer to the plasma state, that means it is taken to such excited state, the monomer is raised to that excited state under very low pressure by creating plasma. What happens? That plasma excites the monomer to form a polymer. Say, what happens if you start with a liquid monomer or a gaseous monomer, that liquid or gaseous monomer will form a solid polymer molecule, and that will be deposited on a substrate in a very organized way, Say, one can get epitaxial growth type of thing, monolayer, double layer, perfectly crystalline thin film. So, that can be done by plasma polymerization. There that you can say kind of photochemical polymerization, plasma polymerization by photochemical initiation, that is also possible. So, those things, those who are interested, literature is available. I have told you the basic principle, you can go through the literature and you can get the details from there. Now, I just mentioned you what is called inhibition of polymerization. What is inhibition of polymerization? Here you see this is a plot of polymer growth versus time. It is a rate of polymerization, nothing but a rate of polymerization. So, in this case in case of normal polymerization, you see the rate is very high, that means percent conversion is, say, 70% conversion can be achieved within, say, 1 minute time, suppose 70% conversion, that means 30% monomer will remain unreacted and 70% of the monomer will be converted to polymer. Now, this curve, look at the curve C, it starts the polymerization from the very beginning, but the rate is not that high as in case of A. That means, the polymer growth is retarded, that means, free radicals are produced that starts polymerization, polymer growth occurs, but at a slower speed, that is called retardation. Now, when this polymerization starts, once the initiation is occurred, if there is no initiation, no polymerization, the growth may be different, growth rate may be different. Now, one case can happen, say in this case, case E, inhibition. B is a simple inhibition, rate is same, but polymerization was not allowed to start. Say in case of hydroquinone, you add hydroquinone to a monomer, store in a bottle, that polymer will not grow, it will stop. Just you have to, in order to start the polymerization, you have to remove the inhibitor. After removal of the inhibitor, it starts polymerization, and this case E, inhibition occurs till this time, then retarded, growth is retarded. So, inhibition followed by retardation, and this is a non-ideal inhibition. So, this is what is called inhibition and retardation. Thank you.